Hi, my name is Lady Savannah, and in this video we're going to work with quaternions. So we're going to learn exemplifying how to find the conjugate of a quaternion, its multiplicative inverse, how to represent a quaternion as a 2 by 2 complex matrix, and how to represent a quaternion as a 4 by 4 real matrix. In the first example, we have that given the quaternion Q, which equals to 3 plus 4i minus 1j plus 2k, we're going to determine the conjugate of Q and the multiplicative inverse of Q. So, the definition of the conjugate of a quaternion says that a quaternion of the form Q equals A plus BI plus CJ plus DK. Its conjugate is equal to A minus BI minus CJ minus DK. So where we keep the same coefficients but change the signs of the vector part of the quaternion. This one right here. This is the vector part of the quaternion. So we are keeping the coefficients but changing the sign. It's like in this, as you see here, this is positive. In here, it's like we are multiplying each of the coefficients of the vector part of the quaternion or imaginary part by -1, as you can see here. So let's start with the first example. We have that Q equals 3 plus 4i minus 1j plus 2k. So its conjugate is 3, which is the same, minus 4i, because here we have positive 4. So it's the negative of positive 4, then we have -4. The negative of c, in this case, c is -1. So we have that -1, its negative is +1, and d is 2. In this case, then we obtain -2. So the conjugate of the quaternion 3 plus 4i minus 1j plus 2k is equal to 3 minus 4i plus 1j minus 2k. So we keep the same coefficients, but in the vector part of the quaternion, we multiply by -1 in each of the coefficients. So in this, we obtain the conjugate of the quaternion. Now, in part B, we are asked to find the multiplicative inverse of Q. Let's recall the definition of a multiplicative inverse. So, given the definition of the multiplicative inverse of a quaternion's Q, the form A plus BI plus CJ plus DK, its inverse is defined as, so this is the notation for inverse, as we already know. So this is its inverse is equal to 1 over the sum of the square of the coefficients. So 1 over a squared plus b squared plus c squared plus d squared. This fraction here times the conjugate of that same quaternion. So we already have the conjugate of this quaternion because we find it in part A. So let's see how this works out. So we have that A, so then Q inverse equals to 1 over a squared, in this case a is 3 squared, b is 4 squared, c is -1, so it's -1 squared, plus d squared, which is 2, 2 squared times the conjugate, which we already have from part A. So we plug in the conjugate here. Now we find the squares of the coefficients in the denominator. So 3 squared is 9, plus 4 squared 16, plus negative 1 squared is 1, plus 2 squared is 4. So we have 1 over 9 plus 16 plus 1 plus 4, all of that times the conjugate, which is 3 minus 4i plus 1j minus 2k. So we obtain that the multiplicative inverse of quaternion Q is equal to 1 over 30 times 3 minus 4i plus 1j minus 2k. So this is how we find the conjugate of a quaternion, step by step. Conjugate in part A, multiplicative inverse in part B. In example 2, we have that the quaternion V equals to 4 plus 6i minus 1j plus 2k. So in A, we are asked to represent V as a 2 by 2 complex matrix. So the complex matrix representation of a quaternion is given by A plus BI, C plus DI, minus C plus DI, and A minus BI. So we have a 2 by 2 matrix. We're given the generic matrix, and we used each of the coefficients of this quaternion. We use it to represent it as a complex matrix. So we have in here that V, quaternion V, equals to 4 plus 6i minus 1j plus 2k. So we have that A is equal to 4, B is equal to 6, C is equal to negative 1, and D is equal to 2. Then by the substitution of A, B, C, and D, we have that the 2 by 2 matrix representation of this quaternion is A plus BI is 4 plus 6i, C plus DI, we plug in C, in this case is C is minus 1, plus DI, in this case D equals 2, so we plug in the 2 in there. Then negative C plus DI, negative C is C times negative 1, we could say that. So we have C is negative 1 times the negative, then we have positive 1 plus 2i, because D is 2, and A minus BI, A is 4, negative B is 6, so negative B is negative 6. So the 2 by 2 complex matrix representation of quaternion V is this one: 4 plus 6i, negative 1 plus 2i, 1 plus 2i, and 4 minus 6i. Now part B is asking us to represent this quaternion as a 4 by 4 real matrix. So we have, it's important to be clear that there are a lot of ways to represent. This means this is not the only way to do it. There are many other different. In this case, we're going to use this one. So let's work with this one for now. So we have that the 4 by 4 real representation of a quaternion of the form A plus BI plus CJ plus DK equals to this 4 by 4 matrix. So A, negative B, negative C, negative D. So what do? We take all the coefficients in this quaternion given here, and we substitute in each of the entries of the matrix. So we obtain the 4x4 VR matrix representation of the given quaternion. So let's check that this is correct. So we have that A is 4, negative B, so B is 6, so negative 6, negative C is negative 1, so negative C is positive 1, negative D is 2, so in here is negative 2, B is 6, A is 4, negative D is negative 2, C is negative 1, C is negative 1, D is negative 2, A is 4, negative B is negative 6, D is 2, negative C is 1, B is 6, and A is 4. So the 4x4 real representation of quaternion V is this one right here. Thank you so much for watching this video, and I hope that you can learn something from this video.